Hello developers, my name is Ajeet Singh Raina. I work for Docker. Today I'm quite excited to show you how to build an AI chatbot from scratch using Docker Model Runner. In case you are new to Model Runner, it is a new feature of Docker Desktop that allows you to run and manage AI models, particularly the large language models locally using Docker. Now, this isn't just another tutorial. We are creating a complete system with real-time metrics, observability, and as well as streaming responses. By the end of this video, you will have a fully functional AI application running entirely on your local machine. So let's jump in. Now, if you have ever built an AI application, this image looks quite familiar. Trust me, a traditional Gen AI development is a nightmare. It is full of fragmented tools, manual integration, complex configuration, and always find AI developers juggling with these model libraries, runtime configs, GPU setups, and dealing with expensive cloud. Now, with Model Runner, things looks quite simple. Docker Model Runner is a new feature which has been introduced in the latest release. It allows you to run an AI model locally. All you need is just three components integrated into a Docker desktop and it should work in harmony. The first one is Docker desktop, which you need to install on your machine. We have a model runner, which you just have to enable under the Docker dashboard, and then you already get a unified Docker workflow inbuilt into it. So Docker Model Runner addresses these pain points which a typical AI developers faces by providing you with a streamlined solution for running these models locally right within your existing Docker workflow. Now, this is how the chatbot would look like, a modern interface based on React, powered by LLaMA 3.2, completely with the real time metrics, Grafana dashboard integrated into it, right? And then we have a distributed tracing. And the best part is that you can see all the matrices right onto your chatbot. Everything runs locally with zero API cost and complete data privacy. So let's jump in. I have already loaded our project here. I'm using IntelliJ for this demo. I have already cloned the GenAI model runner metrics repo from Docker samples GitHub repository. Now, if you access a README file and scroll down a bit, you will see an architecture diagram here. So let's go through this diagram once. You will find that we have multiple components here. You have a front end, back end, observability stack. So front end sends a chat message to the backend API. Backend formats the message and sends to the model runner. Then we have LLM, which processes the input and generates a response. The backend streams the token back to the front end as they are generated, and then the front end displays the incoming tokens in real time. We also have an observability components, which collects all those metrics, logs, and traces throughout the process. Now let's understand the complete project structure. We'll start with the backend. Let's start by looking at our imports. We have the standard Go libraries for context, JSON handling, HTTP, and time management. And then we bring our custom packages for the middleware and tracing. So the key external dependency here are Prometheus client for metrics. We have OpenAI SDK and the protocol buffer definition for metrics data transfer. Notice that we are also using a custom Prometheus rather than custom promises registry rather than using a default one. This gives us a complete control over our metrics and prevents any conflict with other application that might be running on the same system. Now let's begin our discussion with the data structure. So we have a basic message and the chat request types for handling the conversation. We have a message struct which defines the role, either user or assistant, and the content. We have a chat request structure, which is interesting because it supports both your individual messages as well as the conversation history. Plus, it also includes an optional format parameter for markdown output. So our observability structure is also very comprehensive. We have a struct metric log, which captures all your performance data that we care about, the tokens in and out, response time, the especially the time to first token, which is critical for every user experience. We do have a llama cpp metric structure too right here. Now this is specialized for the local model monitoring. It tracks the context window size, the prompt evaluation, tokens per second, the memory usage per token, thread utilization, and batch size. So this gives us a deep insight into our local model performance. Next, we have a metrics summary. It provides you with a clean JSON interface for your front end dashboard, aggregating all your key metrics into a single response. Now, in the next section, we define all our Prometheus metrics using our custom registry. We have several type of metrics here. If you see here, the total number of HTTP requests. So the HTTP level metrics request counters with the labels for endpoints, methods, status code plus the request duration, histograms. Then we have an AI specific metrics here. The chat tokens counter tracks the input and output tokens separately for each of this model. The model latency histogram has custom buckets optimized for AI response time, say from 100 milliseconds to 60 milliseconds. So the first token latency matrix is crucial, right? And you can clearly see here that first time to token in seconds. So user perceives app as faster when the first token arrives quickly, even if the total response time is the same. Now for LLaMA CPP model, we have a specialized metrics here. uh, Context size as a gauge, prompt evaluation time as histogram, tokens per second, memory usage. These metrics helps optimize your local model performance. Now let's jump into a kind of an helper functions here, which we have defined. These functions are essential for extracting the value from Prometheus metrics. So you see a couple of them: the get counter value function, which get you a specific counter by labels or sum up all the counters in a vector. The gauge and the histogram helper handles the protocol buffer conversion safely with proper error handling and back fallbacks to zero values. Then you will find a calculate error somewhere down here. So let me see if I can find. So if you search for calculate, these are a couple of other functions like calculate error rate function, which computes your error rate by dividing the total error by total request with a safety check division by zero. We also have a get llama cpp metrics function, which checks if you have any llama cpp metrics here or not, right, which you can see right here. Now now it's time to talk about the main function architecture. So main function start by loading the configuration from environmental variable, the AI service base URL, the model name, the API, and this makes the application completely configurable for different deployments. The tracing setup, which you see here, is optional and controlled by the environmental variable. And because when you enable it, it connects to the Jaeger instance for distributed tracing across your entire stack. Next, we create a kind of an OpenAI client with custom base URL and API key, making it compatible with the OpenAI local models or any OpenAI compatible API. The middleware chain is elegant. We apply metrics middleware to every request and optionally adding the tracing middleware. This ensures that every request is automatically instrumented. Then we talk about HTTP handler. We have a course handler which ensure that our API works with the web front end by handling the pre-flight options request. We have health check endpoint, which is intelligent. It doesn't just return okay, but it provides you with the model information and automatically detects your LLaMA CPP model. It estimates the context window size based on the model name, which is again useful for your capacity planning. So we have multiple metrics endpoint serving different purposes. We have a standard metrics endpoint for Prometheus scrapping. We have a metrics slash summary endpoint which provides a JSON summary for front end. We have metrics log endpoint which accepts the custom metrics, and then we have a llama cpp endpoint which is specialized for a local model metrics, which you can see right here. There are all sort of these metrics which have been, you know, specified here. Now coming to the server architecture, we have two separate servers here, right? As you scroll down, you will see that the main application server which runs on port 8080, and we have a dedicated metric server which runs on 9090. And this separation is a production best practices which allows you to secure your metrics endpoint separately. We talked about main.go file, which is just an entry point. Now, in a production application like this, you would also have a package directory, which we call it as a PKG, with a reusable middleware for metrics and tracing. We have a backend.env file, which we are going to go through in a little while, for configuration and for supporting the packages for logging and health checks. Now, the beauty is that main.go stay focus on the core business logic, while all the cross-cutting concerns are handled by these supporting packages. Now, in this IntelliJ, I have a metrics.go which is being displayed. So the metrics package under the slash pkg, it cleanly separates all your observability concern from your main business logic. So if you look at the metrics packages, it serves as centralized observability hub for your GenAI application, defining all your Prometheus metrics in one clean location. It exports your pre-configuration metrics for HTTP, all the HTTP connections or operations, which includes your request counters, duration, histogram, the active request, all AI specific operations like token counter, model, latency, first token timing, and also specialized LLaMA CPP metrics, which includes the context size, prompt evaluation times, tokens per second, memory usage, thread utilization, the batch size. So you will see all the specification right here. And this separation keeps the main application logic clean, while you ensure that you have a comprehensive monitoring coverage. We also have a smart metrics categories. This is a package which intelligently categorizes the metrics into the tiers, like a standard HTTP metrics or AI specific metrics or any of the LLaMA CPP metrics that provides deep insight into your local model performance. The custom histogram buckets are optimized for AI workload, as we discussed, from zero point 0.1 seconds to 60 seconds, right? And reflecting the real world GenAI application performance characteristics rather than the generic web service patterns. We talked about front end and back end, and now there are a couple of observability components in place. Now let's look at how all these components come together in production, right? So I have highlighted a Docker Compose file, which basically helps you to build those microservices, and it let all of these components talk to each other. Now this Docker Compose file shows how you deploy a complete enterprise grade GenAI stack with just one command. We are talking about the full observability platform with monitoring, tracing, dashboard, AI model serving, all orchestrated using a Docker Compose file. Now let's talk about the backend service. Now this is our Go application we just walked through, right? We discuss how to configure and to work with model runner. We are exposing two ports here, which is port 8080 and port 9090 for our dedicated Prometheus metrics endpoint. We also added a health check. This health check is particularly important here because we are using wget to ping our health and endpoint every 3 seconds. This isn't just for monitoring, but there are other services which depends on this health check. So the backend connects to our app network and importantly depends upon the LLM service, which we are going to discuss later point of time. And this ensures that our AI model is available before the backend starts. Now let's talk about front end. Front end service is our React TypeScript service. It is built from a front end directory and exposed on port 3000. Here's the clever part. It has conditional dependency on the backend services, which you can see it right here. Now, this prevent user for being seeing a broken interface during the startup. The front end connects to the same app network so that it can communicate seamlessly with the back end without without exposing any internal network details to the outside world. Next comes Prometheus. Now, Prometheus is basically we are talking about the observability magic, right? So Prometheus is our metrics collection system using official Prometheus image here 2.45.0. We are mounting a custom configuration file which tells Prometheus where to scrape the metrics from. primarily our backend port, which is 9090. The common parameter are production ready. We are setting up persistent storage here. Now, if you see here, there are various commands here. So we are setting up a persistent storage. We are enabling the web console, and most importantly, enabling the lifecycle management so that we can reload the configuration without even restarting the service. Prometheus again runs on port 9091 to avoid conflict with our backend metrics port. Next comes our observability stack, which is Grafana. Grafana provides our beautiful dashboard and visualization. We are using Grafana 10.1.0 with pre-provisioned dashboard and data sources. The pre-provisioning directory contains all our dashboard configuration, so your monitoring setup is completely automated. No manual clicking through Grafana UI. So here we are setting up a default admin password, disabling the user sign up for security, and then running on port 3002 so that it doesn't conflict with other tools like OpenWebView and all this thing. Grafana again depends upon the Prometheus because it needs that data sources available to the function properly. The persistent volume ensure that your dashboard customization survive the container restart. Finally, we have a Jaeger. Again, it is an optional, but we have added this because it handles our distributed tracing, crucial for debugging the complex GenAI workflow. So we are using all in all image, which includes the collector, the query services, um, and a UI in one container, perfect for development and a small production deployment. The key ports here are 16686 for web UI, where you can visualize the traces. We have 4317, 4318 for OT, LP endpoint. And remember, in our Go code, we configure the tracing to send to Jaeger 4318. This is where your traces end up. So this gives you a complete visibility into the request flows across your entire stack. Now, the next service is the game changer. It is a service which doesn't run as a container but on the host system, and this is a really exciting part. Now, this is a new LLM service using Docker Compose model provider. This is Docker's new native AI model support. Instead of manually managing the model containers, Docker Compose now provisioning this AI model directly. So we are specifying the model as LLaMA 3.2, which matches our backend.env configuration. Now, this is the same model format which we used by Docker model runner. The beauty here is that Docker handles the model lifecycle, downloading, loading, serving all automatically, right? And then we have a network, and the volumes, everything connects to app network bridge network. This creates an isolated communication in between the services while allowing the selective port exposure to the host. The backend can talk to LLM service, Prometheus can scrape metrics from backend, Grafana can query Prometheus, Jaeger can receive traces, all through the internal networking. The only port exposed to your host machines are the one you actually need to access is 3000 for the front end, 8080 for the back end, 9091 for Prometheus, 3002 for Grafana, and 16686 for Jaeger. So everything else stays internal, secure, and the entire stack comes up with just one command: Docker compose up. That's it. Now, to see it in action, ensure that you have already installed the latest version of Docker Desktop, ensuring that it is Docker Desktop 4.41 plus. Now, once the installation is successful, all you need to do is go to the settings, beta feature, and you will see an option called as enable model runner option. You just enable it. Don't forget to enable the host side TCP support and keep the default port to 12434. Next, we need to enable AI models. So we have an model option on the sidebar. Just like viewing the containers, you can manage your downloaded AI model directly in Docker dashboard. Here you can see the model details, storage, usage, and even manage your local AI model library. Now, to save our time, I already downloaded the LLaMA 3.2 model. Next, all we need to do is get into a project root directory and say Docker Compose up. Wait for all those compose services to come up gradually based on the sequence they'll come up. Now, within few seconds, you will see that the chatbot is ready. You can access it with port 3000. Just go to the browser and open up localhost 3000. Once you open it, you will see that it looks very similar to how the ChatGPT look like, but a minimalistic version. But one thing which is really promising is that like we have an advanced metrics right on the chatbot, the input output tokens, the error rate, response time. You will also see the model name displayed on the top. Now, if you look closely, you will find that a metrics dashboard is right there. Okay, but before we get into the metrics dashboard, just go ahead and start chatting with the chatbot. You can type hello, and it gives you a kind of a response. Next, I can type saying like, okay, write a poem on Docker and AI, and it gives you the response. And you can see the changes which is happening in terms of input and output token. Now, as we were talking about the observability stack, right? Let's click on that view detailed metrics dashboard, and it will redirect you to Grafana login page. Grafana is a visualization tool which allows you to visualize the metrics through the customizable dashboard. Click on the view detail dashboard. Now, once you get a login page, you just have to enter admin as username and password. Even though most of the Grafana installation and the configuration comes with some kind of a pre-configured, dashboard. For in our case, I'm going to show you a quickly like how the Prometheus dashboard can be added quickly. All you need to do is under the data source, choose Prometheus. Now here, one thing which is really important is that most of the time it happens that you add localhost 9090 as a standard port, but since now Grafana is talking to Prometheus by the service name, so we need to add HTTP Prometheus 9090 as a port, as a Prometheus server URL. Now scroll down to the end of the site and you say save and test. By now you should see successfully queried Prometheus API as acknowledgement. Select the dashboard, click the re-import for all this dashboard. By now you should see a Prometheus 2.0 stats dashboard up and running and displaying all the metrics that is being fetched from the backend exposed API endpoint. We already saw Grafana dashboard. Let's look at what metrics does Prometheus collect. Now, looking at the Prometheus metrics for your GenAI model runner, you have got very fantastic observability into your LLaMA CPP performance. Now, if you just try to search with GenAI, you will see that all those metrics related to the LLaMA CPP. The LLaMA CPP, especially the context size metrics, right? It is crucial because it shows how much the context window your model is currently using. This directly impacts your memory usage, the processing time. The larger the context means the more computation overhead, but better conversation continuity. You can use this to monitor whether your applications are hitting the context limits or not, or if you need to optimize your context management. Next one is your token generation performance metrics. This is where your things gets really interesting. This gauge shows how your model real time throughput, essentially how fast your AI is thinking or even generating the response. Meanwhile, we have a prompt eval seconds metrics, which tracks how long it takes to process the initial uh, prompt before generation begins, right? And this is critical because the prompt evaluation is often a bottleneck, especially with the longer prompts or complex instruction. You'll also see a latency metrics here, which measures the time from request to the first token generation. This is what the users actually feel as a response time. These bucket style metrics lets you create a percentile charts in Grafana so that you can see not just average response time, but the worst case scenario. Now, combined with all those Gen AI app active requests, you can correlate the latency spikes with high concurrency periods. If you enjoyed this demo and want to see more, be sure to like this video and subscribe. We will be sharing even more ways to showcase Docker's exciting features in upcoming videos. Till then, have a nice time building with Docker. Thanks for watching this video.